Hi, welcome to this session. The freedom of Kubernetes requires chaos engineering to shine in production. So obviously, if you're connected to this session, there is a big chance that you are interested in Kubernetes and also in chaos engineering. So take a glass of water, a glass of coffee, enjoy yourself, relax, and let's spend half an hour together. So before you start actually to the main content, I would like to briefly introduce myself. So my name is Henrik Rexed. I'm a cloud native advocate at Dynatrace. But prior to Dynatrace, I've been involved in the performance engineering market more than 15 years. And as a result of that, I have become one of the producers of one of the YouTube channel dedicated for performance engineers called PerfBytes. So check it out if you're looking for content for performance engineers. On the other hand, last year, in July 2021, I started a new fresh YouTube channel called Is It Observable? It's a dedicated YouTube channel related to observability in general. So if you're looking for content, tutorials, content that will explain a given framework or technology, check it out. It will be really helpful. And I also looking for feedback. So please connect and send me your feedback. So what are we going to learn if you stay with me on the next 30 minutes? So a couple of things. Because we're going to talk a lot about Kubernetes and the challenges and the problems that we could probably face in production, it makes sense that we do some couple of reminding related to Kubernetes. We will, of course, present the challenges itself. And then to validate that, we will use chaos engineering. So we'll introduce what is chaos engineering and then see what will be the experiments that we will need to design to be able to validate our Kubernetes settings. Last, we will also, because we do some testing, we also need to have observability in place. So we'll see what type of metrics and events we will need to collect to be able to validate our experiments. And last, we will briefly explain how we could automate that process. So the dark side of Kubernetes. So Kubernetes is an orchestration framework. Everyone knows it, no surprises. And in Kubernetes, there are two types of nodes. In fact, Kubernetes relies on nodes, and nodes at the end are physical servers and virtual servers, or virtual servers. The master node is one of the nodes that is in the top in this slide. As you can see, there are various icons. You can see the scheduler, etcd, control manager, and the API server. So the master node, if you're using on any managed Kubernetes environment provided by any of the hyperscaler, AVS or Azure or GCP, then you probably don't see that master node. If you do manage fully the cluster, you will have to manage as well the master node. On the bottom, you have the workload node. The worker node are there to basically host our workload. So when we deploy any workload within our cluster, Kubernetes will basically move our workload in different state. And behind that, there is a lot of events. And I need to remind those process because it's very important that to understand the various challenges that we're going to talk to in a few minutes. So when we deploy using kubectl or anything else or maybe other systems, the first step of deploying our workload will be in pending state. So pending state means Kubernetes knows it has to deploy a new workload, so it will try to identify a node that is able to host that new workload. So based on resources, based on taints and tolerance and various policies. Then once he has identified the right node, then our workload moves to the creating state. Creating state means I know which node is going to host my workload. And because our workload relies on containers, at that state, Kubernetes will basically interact with our Docker registry to pull out the images and validate that there is all of the requirement that is needed. If we have any volumes, if you have any config map, any secrets, it will check that those exist to be able to deploy it. Then, once we have all the requirements are there, then our workload is in a running state. So it doesn't mean that it's officially running. It's just that Kubernetes has started the pod with the various containers in it. And if you want to check if the app is obviously running, you need to check all the readiness probes or health probes that Kubernetes provides. All right, so now you know all the various states of our workload. Once upon a time, Kubernetes killed my workload. All right, so here let's say we have a cluster. I have two applications, so I've decided to have two pods. Let's pretend that it's not two pods, but two namespaces with a lot of various pods inside of them. And I have more than one node. So here we see only one worker node. And during that time frame, one of the app was basically consuming more resources. And as a consequence, there were almost no resources left for the other workload. And as a consequence, to be able to avoid any node pressure events or infrastructure issues, Kubernetes will try to resolve that problem. And for that, it will start an eviction process. Eviction process means it's going to select one of the existing pod running in that node, and it will evict it. Evicted means first I kill the pod from that node, and then I reschedule it on an available node that can take that new pod or that new workload. So here, in few minutes, we were able to resolve our pressure situation, and our user were almost not impacted. But it could be worse. It could be very, very worse. Imagine that all your nodes are pretty much saturated, or you have designed some tense and tolerance policies, and there is no nodes for your workload anymore. And so you have killed the workload from the previous node, and that node, that new workload is not able to be scheduled elsewhere. So basically, no app, nothing responding to our user. So here, it's pretty critical for us. So we need to figure out how we can avoid that type of critical situation. So how can we do that? Well, for that, they are, they say, the recommended Kubernetes approach. So first, eviction works by quality of services. So we need to define requests and limits in our pod. So by doing this, Kubernetes will basically determine a specific quality of services related to our requests and limits. So if our requests equal our limits, then our workload will be considered to be guaranteed. If the request is under limits, then we are burstable, and there's nothing defined. It's best effort. When the eviction happened, the eviction will happen in that order. So first, it will try to delete the best effort, then burstable and as guaranteed. The second recommendation, of course, is to put resource quotas in our namespace. Remember our situation where the app were eating the resources of the second app. If I want to avoid that, because we usually silo our apps based on namespaces, if I define resource quotas on my namespace, then I'm pretty sure that I won't be able to have that situation, because my app will basically have dedicated resources and it won't be able to eat more. So request and limits is a hot topic in Kubernetes. So let's have a look at the request and the limits. What is the value of that and how you can express it? So first, request. Request is a bit like Tetris game. So Kubernetes behaves like a Tetris game. Remember, you have shapes going down from the screen. We move them and we place them on available spots. And the idea, we want to make lines. It's the same thing with Kubernetes. Kubernetes, we deploy, we have a new workload. He sees the workload coming in. And then based on the size of the workload, so the request, he will try to place it on the right node. So basically, request is there to tell to Kubernetes, okay, I need at least 100 megs to run my workload. So he knows basically the shape of your pod. So he will be able to play Tetris. If you don't precise any request at the end, Kubernetes doesn't know the shape of your workload. So he sees a small square, he places it somewhere, and then suddenly that square becomes a huge shape. So impossible to play properly the game. We can also imagine that Kubernetes is a bit like a box of chocolate. Remember when you're kids, you receive a box of chocolate. Of course, you don't read the manual. I mean, who reads the manual today? But we pick the chocolates and then we eat it, and suddenly we discover there's liquors. And remember, we were making those faces, I don't hate liquors, whatever. Maybe today is different, but it's the same thing. If you don't precise the request and limits, it's the same thing. Kubernetes will take the chocolate, it will imagine that it's a chocolate without liquor, and then he starts to deploy it, and he realizes there's liquors inside of that. So putting requests is very helpful because it helps Kubernetes to properly orchestrate your workload. So how do you express it? CPU, of course, in MIDI cores, and memory in bytes. Nothing complicated. If you do the right test, we know what will be the minimal resources that we need to run properly our applications. Of course, you can put very high values, because if you don't want to test and you want to basically guess, yes, you can do, but keep in mind that those resources will be allocated by Kubernetes and they will never be used. So at the end, you're not optimizing the usage of your node properly. The second concept is limits. So now we have defined that we need a 3-room bed apartment. And now we have a contract with Kubernetes saying, okay, so you have the 3-bedroom apartment, it's fine, but you won't be able to consume more power or more water during some period of the day. So that's basically the limit. So we have a contract with Kubernetes saying how much resources can I officially utilize in that cluster, in maximum, what will be tolerated by Kubernetes. So for that, we can express it for the memory in bytes. So this is very useful, very easy. I do a load test. I can see what's the maximum value that I need for memory, and so that I can basically guess it. On the CPU side, it's more difficult, and this is due to the fact that we have an heritage from the Docker world. So the way Docker works to share resources within our host, it uses a CFS, and for this, the CPU basically is split in function timing. So let's say that one core has periods of work of 100 milliseconds, and we're going to determine the quota that we can use within that period. So we have 100 milliseconds of CPU period, and if I defined, let's say, 20, I will be able to consume only 20 milliseconds. So basically, I do some work, I consume 20 milliseconds, then the node or Docker will basically pause my work and wait until the next CPU cycle, and then I will be able to resume my work at least for 20 milliseconds, and so on and so forth. And that mechanism to be paused during our work means throttle, so CPU throttled. So if I define my value too low, as a consequence, I will get a lot of CPU throttling. And if in the memory, if my value too low, then Kubernetes will kill my workload and send an event called omkill. And if we don't input the value too high, at the end, we are not optimizing properly our resources in our cluster. So that's why it's really important to define it properly, those limits at least, because in the memory, we can see that Kubernetes can kill our workload. And if in the CPU side, basically we are throttled, and as a consequence, our workload will be very, very slow to be able to work properly. In fact, it's funny because when I started to work with those request and limits, I said, hey, let's do a test. So I said, let's remove all the limits from our workload, run it and measure on the response times in one end and on the resources. So you can see on the graph on the top, it's a CPU usage. You can see that without, I was able to consume almost 650 millicores. And when I applied limits, you can see that my resources, I'm consuming way, way less resources. It's normal because I have a limit defined. But now let's have a look at the actual experience that we're giving to our users. In the bottom, you can see response times. As you can see at the bottom, we have we have a response time that is about 100 milliseconds or less. Pretty good. But then when I apply the limits, boom, you can see that we almost have 3.6 seconds of response times, which is very, very high. And this is only due to CPU throttling. So what do I need to put CPU limit in my cluster? Because at the end, it seems that it works better without it. Well, because it's a best practice for the industry. At least for the memory side, you need to define request and limits. Otherwise, you won't utilize properly your resources and your nodes. And for this topic, request and limits, there is tons of horror stories available on various presentations done in KubeCon. So here you can scan the QR code. There comes to a website listing all those horror stories. So we'll definitely recommend to watch it. There is plenty of interesting stories, performance issues related to CPU throttling, Airbnb, Zalando, they talks about it. Stability issues due to omkill, same thing, Airbnb, Zalando. So check it out. You see that you can learn a lot of things, and this topic is very important because at the end we know that we can have a major impact on the stability and the behavior of users. So how do we validate and avoid that type of situation? Well, obviously chaos engineering. So what is chaos engineering? Chaos engineering, if I took the definition from in Wikipedia, you say chaos engineering is a process to discover vulnerability by injecting failures and errors. And it even says in production. So first of all, don't do it directly in production. You don't improvise in production. So first you do it in a non-production environment. And then once you're mature enough, you move to closer to a production environment. So let's have a look at the various workflow. How do you define those errors and vulnerabilities in our environments? So first, the process is in our 3 steps. The first step is we need to define hypotheses. So we can say, okay, I've designed my app, I know the architecture, I know the system, what could go wrong? What could fail? So basically, for example, I have a connection to a database, I may assume that I can basically have a network connectivity issues between my system and database. That could be a problem. Then I need to predict how my system react. Either it will basically handle properly because I've designed an awesome architecture, an awesome design of software, okay, or I can also predict that, okay, my system is going to fail or have some problems to write to database. So okay, we need to list basically what we expect from that situation. Then we need to define what are the metrics and events, whatever, that we need to collect to be able to validate our experiments. And then we define our experiments. Usually an experiment is a workflow of tasks. So first, I want to inject latency between my app and my database, or I want to inject, let's say, packet loss, whatever. Basically to simulate network problems. I can restart my app. Basically you define the workflow of this given specific situation that you want to test. Keep in mind, then we need to define how to roll back. Why? Because keep in mind that we're going to run that probably in production. So if in case there is a problem, we need to have the process described and automated to be able to come back to a normal state. And then we also need to figure out how we're going to collect the various KPI that is required to validate our experiment. And last is basically we run our test. All right, so what are the hypotheses related to Kubernetes? Remember, we talked about it, request and limits. So what are the various hypotheses? So well, for this, well, I got some ideas. So first, we have Kubernetes settings. We know that if I change request and limits, I have an impact probably on my users. So I want to basically validate that those settings are working fine. So my expectation is that, yeah, Kubernetes is good. I've already defined the right request and limits. So I expect that my app is stable, performance, no impact, and no error rates. Okay, fine, fair enough. Then you have the maintenance scenario. What are we referring to maintenance, by the way? Remember, when you have to upgrade your nodes, because nodes at the end are a physical or virtual servers like I mentioned. So if you want to upgrade the version of Kubernetes because you're upgrading your master nodes, then to do that, you will have to node drain. So you remove that node from the actual work, you do your maintenance task, and then you reattach it to the cluster back. So this is a maintenance task. It will clearly happen during your production hours or night hours, but as an expectation, I say if I have designed well my cluster, I should have no impact. Stable, no user impacted, everything works smoothly. And last, it's a story that we had before, eviction. So we're turning into a node pressure or a situation where we come into the situation where there's an eviction. So my expectation is that because I've defined the right priority on my pods, no downtime, stable and performant, no impact on my users. What are the observability pillars that we need to collect? Of course, in observability, there is plenty of pillars. You have logs, you have traces, you have metrics, you have Kubernetes events is also one of the pillar, and then you can add profiling and others. But here, in our particular case, because it's pretty much related to infrastructure topic, we will focus on metrics and Kubernetes events. So let's have a look at those metrics and events that make sense for us. So first, let's have a look at the metrics. Keep in mind that Kubernetes is like applications are a bit like an onion. There's the different layers. So first you have the layer outside, which is the user. So the user is interacting with our app. So I will probably collect some metrics about the user. So response times, failure rate, basically user experience. Then I will go to the next layer because Kubernetes relies on nodes. I need to figure out how my nodes are behaving. So in terms of resources, so CPU, memory, number of pods running on that specific node, maybe also number of ports available, IP address, and so on. A pod, so within that node, I have pods running in that. So here I will keep track on what I have defined in terms of requests and limits for my CPU and memory, what is the limits, and what is the actual usage. So then I can figure out if I'm far from the limits or not, so I can optimize that settings. And last, in the pod, I have some containers. And remember, CPU throttling is a Docker concept, so we need to measure that from the container perspective. So we'll look at the CPU throttling, the memory usage, and CPU usage, of course. On the event side, as we saw at the beginning, there are various states in Kubernetes, and in those states, there are different type of events that is sent by Kubernetes. So of course, the user won't send any major events except maybe tweets or a support case. But we are focused on mainly on the events coming from the cluster. So the node pressure, that is a sign of a problem. On the pod, I could say fade scheduling. That means that we are not able to place that workload anymore on any of the nodes. That could be a really important sign. Eviction, of course, OM kill, unhealthy, that type of events. So what are the kind of experiments that we need for Kubernetes? So first, we're going to test the evictions and the maintenance scenario in the same one. Why? Because I probably have a lot of nodes. So to be able to come to the situation where I'm putting high pressure on my node, I want to remove some nodes. So I'm going to have less nodes than expected because I want to come to the situation where I'm having a node pressure. So our first node drain, and then I will then simulate CPU stress on the node, memory stress on the node, and I will generate some load test because I'm not going to run it in production for this type of experiments. I want to run it in a non-production environment, and I need to measure the impact on the user. So I will run a constant load, so no spike test, nothing fancy, just the load test will only be there to report how is the actual response time from the user perspective and what is the error rates, what's the stability of the applications. On the Kubernetes settings and I may not need necessarily some chaos experiments. I can, if I want, I can do it to be able to come to the right situation. But usually just a standard load test is fair enough. You run the test, stable load again, and you measure the response time, the failure rates, and you compare it with requests and limits, without. You measure the CPU throttling, and you tweak those settings to at least get the right settings that will provide the highest response times and with the right stability of our apps. So what do we need for this? So first, I will need a Kubernetes cluster, and there is various tools that are going to deploy. Here you can see that I have two colors here, the nodes I've separated. I want to make sure if I run the experiments on the same cluster as my app, I want to make sure that the experiments are not impacting my tooling. So I need an observability backend solution, Prometheus or Dynatrace. I need a K8s engineering tool. So in my case, I use Litmus, and a load testing product. I use K6 in my case. So for this, I have labeled the nodes to make sure that all the toolings that I need for my experiments are placed on dedicated nodes. And then I have other nodes that are dedicated for my app, and I know that my experience will only impact the nodes for my app and not my testing tools. Then, like I said, I need some tools. So I need a K8s engineering product. I use Litmus K8s, which is a part of CNCF. Really good product, by the way. There's a web UI called the K8s Center. So Litmus K8s can be installed either in the same cluster as your app, or it could be installed on a dedicated cluster, and it will interact with your cluster where your app is running. For this, in any case, you will need to deploy an agent either on the same cluster as Litmus K8s, or if you have a remote cluster, you will have to install the agent that will come with the K8s exporter. The K8s exporter exposes a couple of metrics related to our experiments in a Prometheus format. And then there is a lot of chaos workflow and so on. I'm not going to go in details on the architecture, but at least keep in mind that those components, the one I'm showing here on the screen, are the main ones. What is great with Chaos, Litmus Chaos, is that there is a Chaos Hub. That Chaos Hub provides 50 plus experiments in Kubernetes. And all the right experiments for our case, which is node drain, I need node CPU hog, node memory hog, all are there. They are already there in the Chaos Hub, so it's perfect. So I don't need to reinvent the wheel. I can simply use it. The other advantage of Litmus Chaos is that it's rely on Argo workflow. So I can define a really specific workflow combining pure Chaos experiments and load tests with K6 in parallel. I'm picking K6. Why? Because K6 has an output extensions that I personally like. It's their Prometheus integration. So K6 provides results that is sent in the command line and the std out or in JSON or other format. But in my case, I want K6 to write into Prometheus the statistics. So then I will have all the observability in Prometheus or Dynatrace, because Dynatrace will be able to scrap the data from Prometheus. But at least I need the response times, the requests, the failure rates, and I also want to have also all the data related to the health of the cluster itself. For this, I will also have a Prometheus in my cluster. If you install the Prometheus operator, it comes with several components. So of course the Prometheus stack, it's the stack, but also a couple of exporters. The exporters is the component producing metrics. So we'll have the kubeset metrics to see how the various objects of Kubernetes, the node exporter, anything related to how healthy are my nodes, CA advisor to collect CPU throttling metrics on the container level. And then I have an exporter for Litmus to be able to collect metrics from the Litmus perspective. And I have an exporter for K6 to be able to collect the metrics from K6 perspective. And those, with Dynatrace and our components, we will be able to collect the right metrics and push it back to Dynatrace. So now you know all the toolings, and let's have a look at how we could automate this process. To automate this, we can define obviously a pipeline in Jenkins or any CI/CD system that we have. So we're going to build, we're going to deploy our exporters. We're going to configure Dynatrace or whatever it is. We can do it because there's all those tools could be configured with API or with command lines. And then I'm going to run my test. Fair enough. But then after the test, someone needs to approve. Someone needs to look at the results. So it's not automation anymore because we have a pose here in this automation. So how can I remove that pose? Well, for this, I'm going to use another CNCF project called Captain. It's an open source solution provided by Dynatrace. And Captain provides several use cases. So first, you have the progress delivery. So you can basically give the power to Captain to deploy, manage, test, similar to a CI/CD process, and also manage production use cases like auto-remediations and so on. Or I don't want to use everything. I just want to rely on my traditional CI/CD system. I just want to use Captain for quality gate, and this is the use case I'm gonna use. Or last, I can use pure SRE and production use cases, which is auto-remediation. Captain is very easy to configure. It's based on files, on YAML files. So you have a ship your file, SLO. So we need to define the SLI, define SLOs in Captain, and those will be used, you see, for the quality gate perspective. And then we can connect our tools. Captain is in a framework based on cloud events. So basically, it's an event-driven framework, so it's very easy. So I can easily disconnect tools, and the beauty is that all the tools I'm going to use is part of Captain. So if we look at the pipeline that we had a few minutes ago, so I'm deploy, I run my test, and then just when I run the test, after the test itself, I will basically send to Captain, and there's an API to say, an event to say, hey, Captain, I just finished the test. Could you evaluate the environment during that time frame? So I've already expressed a couple of SLI and SLO. So Captain will reach out to the SLI and SLO that we've defined for that particular services. And so you say, okay, so pod failure needs to be 100%, node pressure under 1%, and so on. So you define basically what you expect. once he looks at all the SLI, he will reach out to the observability backend that has the value, so either Prometheus, Standard Trace, and then he will look at the values and match it with the objective that we have defined. And then he will basically present the results of each individual SLO that we've defined into a heat map, like you can see here. And the great thing is, at the end, it provides a score. And at the end, I will have one SLA based on the score. So we say my experiments were fine if we have a score of 90%, for example. And that will be basically in 1 minute, unless my test ends, Captain trigger all that workflow I just described, gets back the scoring, and from the scoring would say, okay, everything is green, or in the other way, everything is red. So let's have a few quick takeaway here. So a couple of things. So first, in Kubernetes, define quotas, resource quotas to separate the namespaces. That is a really high recommendation from the Kubernetes world. Define QoS, so requests and limits. We talked about during a long time. Observability, of course. We need to collect metrics, logs, traces. We need to understand what's going on in our environment. So make sure to have everything. SREs. So, of course, define SLI and SLO. I mean, we want to be smart. We want to automate. So without SLI, SLO, it will be very difficult to be efficient. And last, we know that we have problem related to Kubernetes. We could face problems related to Kubernetes. So let's test them utilizing load test and chaos engineering to validate that our cluster is stable, our users are happy, and there is no surprises in production. So before we actually finish this presentation, I will do another quick promo to my YouTube channel, Is It Observable? So check out the various episodes there. There is one dedicated to Litmus Chaos, to chaos engineering, performance testing, and so on. So check it out. And yeah, I'm trying to improve the content. So if you can send some feedback, that will be great. So then I can continue producing content and help you guys in your project. All right. So thank you for your time and enjoy the conference.